starting off right here. So if we look at it, basically what we got is we have white light. And that's what we're going to talk about really quickly. It's just about white light. When it comes to white light, we're all pretty familiar with the fact that, hey, white light is actually made up of a Roy G. Biss spectrum. So that's a rainbow of colors. And when these rainbow of colors come towards our eye, what we see, of course, is going to be white light. We don't see the breakout of the actual Roy G. Biss. But at the same time, if we take the white light and we push it through a prism, then what's going to happen is we'll see that nice little Roy G. Biss spectrum being produced here. So, just in case you have not seen it, which I'm sure all of you have probably seen this before, what you have on your desk, well, a lot of you have on your desk, is going to be this device that looks like this right here, which is a spectroscope. You're going to take the spectroscope, you're going to look through this little opening right here. You'll hold it up to the actual light, and then you're going to look inside of it, and you should see a Roy G. Biss spectrum. Now, what you're going to notice is some of you have a circular one that's sitting on your table. It's kind of like a silver color one. The same thing. You'll look through that actual ocular right there, look up, and when you look up there, you should see the Roy G. Biss. Now, if you don't have one, then pass it to your partner. Be generous, let them see it as well. But hopefully you see the rainbow of colors, right?
Wow.
So it should almost look like these Skittles of colors here. Taste the rainbow. Wait a second. Taste the rainbow? How are rainbows actually produced?
Isn't it prism off the water droplets?
That's exactly it. Once you get the water droplets up in the atmosphere, they act as a prism. The light comes through the actual water droplets and it produces the beautiful rainbows that we see in the sky sometimes. All right. And contrary to what people might think, you can try to follow the end of the rainbow, but guess what you're not going to find at the end there? All right, you're going to find that leprechaun sitting there. All right, here we go. Continue on. Once again, passing the actual white light through the prism, we're going to see that rainbow color. But what is unique is what if we take something that is non-white light? If we take something that is non-white light, such as a magenta, and when I think about the Roy G. Biss spectrum, there's magenta on the Roy G. Biss spectrum. Magenta is actually made up, in this case, of red, blue, and also some violet. If you're ever in an art studio and you kind of mix those colors together, you're going to get a magenta color in this case. Now, when these colors are coming at my eyes, once again, I'm going to say, oh, I see magenta. But at the same time, if I take this color and I pass it through the prism, then it's going to break it out into the corresponding colors that actually make it up. Now, why am I talking about white light? Why am I talking about this colored light? Is one of the things that we're going to see is that when it comes to elements, if you give them either heat or if you give them electricity, it is possible for that element to say, hey, within that electricity or heat, I see the quantum of energy I need in order to promote up to the excited state. So it'll jump up and become excited. And when it jumps back down, it's going to say, hey, here goes a photon of color. Another electron might say, well, I'm jumping up a little bit higher because I got that quantum energy. Jump down, I'll shoot out a photon. But if you look at an element, what you might get is you might get one element that's pushing out 1, 2, 3, 4, 5, 6 different photons. Now you might say, well, wait a second, these are both reds. One of the things we're going to see when we do this activity in class is that when it comes to red light is made up of a certain wavelength. And it's not just one specific wavelength. It's from one wavelength to another wavelength, and you'll get the actual red light being produced here. So these are just two different wavelengths of red light. Now, if I look at this particular element, and I study the colors that it can produce, one of the things we're going to see is that it's a unique color that will only be produced by that element. Now, there might be another element that when I look at the color after I put it through electricity or if I give it a flame source, it might also produce something that looks like a magenta to my human eye. It's like, how am I be able to tell the difference between these two elements? They both are producing magenta light when I look at them. When we look at it through a spectroscope, one of the things that you would notice is even though, hey, this looks like magenta to my eyes, the other element might have something like this. Instead of 2 bands of blue, it might have 4 bands of blue. Where this one might have a grand total of maybe 5 or 6 bands of red in this case. It's going to be different. No two elements are going to end up having the same bands of colors when you heat them up or you run them through electricity. Which means that because it's unique to each element, then we've got a way to actually identify the element. It's almost like a fingerprint in this case, where I can just look to the actual spectrum, which I'll show you in a second, which is called the atomic emission spectrum of an element. No two elements are going to share kind of this unique pattern of colors being produced. Now, what I do really quickly is we're going to watch this really quick video that kind of talks about it as well. So let's see if it's going to work here.
Bohr said that when an atom was heated, its electrons would become agitated and leap from one fixed orbit to another. Each downward leap would emit energy in the form of light in very specific wavelengths. And that's why atoms produce very specific colors. This is where we get the phrase quantum leap.
If it weren't for the quantum leap, you would have this smear of color coming out from an atom as it got excited or de-excited. But that's not what we see in the laboratory. You see very sharp reds and very sharp greens. It's the quantum leap that's the origin and the author of that sharp color.
Bohr said,
And here we go. So if you look at it, what you're looking at right now is what is called an atomic emission spectrum. Atomic atom. Emission because it's emitting, in this case, these photons of light. And it's a spectrum that represents the various colors that you're going to see here. And what you'll notice is that, hey, we got sodium, we got hydrogen, we got calcium, magnesium, we got neon. But one of the things you'll notice in the spectrum is none of them share the exact same patterns of light that's being produced, because every element has its own unique pattern in this case. And if you look at hydrogen, one of the things you'll notice about hydrogen is it has this band of red here. It also has a green, a teal, and also a violet. Well, guess what I have right here? I've got hydrogen inside this gas tube. And what I do is I'm going to actually run some electricity through it. And when I run the electricity through it, what I want you to do is I want you to look through your spectroscope up here at the hydrogen and see if you can see the band of red. You should see the green, hopefully the teal and the violet as well. But once again, this is something that is unique to hydrogen in this case. And when you have the circular spectroscopes, sometimes you got to rotate it a little bit. So as you're looking through it, kind of just rotate it slowly. If you have the black one, sometimes you got to move it either right to left. Depending if you have it horizontally, just kind of move it right to left. If you have it vertically, kind of move it like right to left until it becomes focused. You'll see it. And then when you're looking through, kind of look to the right inside the spectroscope or to the left, because it's going to kind of shoot it over to the right or the left inside of it.
Whoa. Oh, I see it.
And you should see some of those distinctive bands. If you can't, if you're in the back and you're having a hard time just trying to get this far up, you can move up a little bit, come up a little bit until you can get it in there. So if you need to come up a little bit, just all need to do it. Once again, that's unique for hydrogen. And keep in mind, one of the activities eventually we'll do is eventually I'm going to have a whole bunch of gas tubes here. I'm going to have you kind of write down the fingerprints of each one of the different elements. Then I'm going to mix up all the gas tubes and put one of the gas tubes in there. And then I'm going to say, oh, well, you know what? This color of bands I'm seeing matches up with one of the fingerprints, and you can identify the element in this case. All right. And once again, you'll get another chance, because eventually we're going to do an activity probably either later on this week or definitely next week. All right, what I'm going to show you now is I told you that if we want the electrons to actually excite up, we had choices. Either we can go with electricity or we can go with heat. Now, let me point one thing out here. When it comes to this gas tube is really hot right now. So I'm not going to reach in here with my hands and actually pull it out, because if I did, I would probably end up burning my hands. Which means that we're not just getting visible photons that are coming off of this thing. We're also getting infrared radiation. Remember, infrared radiation is heat. Unfortunately for me, I can't see infrared. There's a little bit of UV radiation coming off of this as well. I can't see it either. The only region of the spectrum that we can see is going to be the visible light. But the one thing I want to point out is, once again, there's just other photons coming off I just can't see in that region of those photons coming off. All right, here we go. What we're going to look at now is we're going to look at using a little bit of heat here. There we go. Now, for this one, you don't have to look at the spectroscope. I just want to kind of show you something. It's pretty cool. And then you're going to tell me where this is actually used. If I take some strontium and I put some strontium on this stick, you're going to notice that it's going to produce kind of this reddish sort of color going on here. But at the same time, if I take something like copper and I put copper on the stick, you're going to get this color right here. And if you think about it, where can these beautiful colors actually be used?
Fireworks.
Exactly. That's exactly where they're being used. They're being used in fireworks. So a lot of times with fireworks, what they'll do is just pack the shell with different sort of elements that are going to produce the colors that they desire, shoot it up in the air, and of course you get the heat from the actual fireworks, and then you get the beautiful spectrum of colors being produced in this case. Now, let me point another thing out here. When we look at these spectrums that we have, once again, these unique fingerprints for each one of these elements, sometimes what they like to do is instead of looking at the whole entire spectrum, sometimes they like to go in and they like to focus in on one photon. And let me explain why they're doing this. Sometimes what will end up happening is only hydrogen might be able to produce a red photon of this given wavelength. Even though these have reds here, you'll notice their reds are not at the exact same wavelength, in this case it's hydrogen. So a lot of times what they'll simply say is, well, that wavelength can only be produced by hydrogen. So I don't necessarily need to have to go looking at these other ones as well. I'll just focus in right here. And once again, that's a way in which they can actually identify elements. To give you an example, helium. Helium was not discovered here on Earth first. Basically what somebody did is somebody actually took their little spectroscopes, they looked at the sun, and they were like, wait a second. I'm seeing a photon of visible color that is not associated, in this case, with any element on the periodic table. The only way that's possible is there must be some element on the sun that has not been discovered here on Earth. When they discovered it here on Earth, they looked at it and were like, okay, that's the same photon that I'm seeing up there on the sun. And that's how they were actually able to discover, once again, helium first on the sun, and then they eventually discovered it here on Earth. Another thing just to point out, this is going back to first semester. And remember in the first semester, I showed you this thing which we said was useful. Where did it go? Go back right here. Where am I? Use the instrument, empirical formula. There it goes. The atomic absorption spectrum, or spectrometer. If you remember, I told you this instrument was actually really useful. And I told you that it was useful for the point that if we take our unknown sample, we can put it in the spectrophotometer. And the spectrophotometer will simply say, hey, this element is made up of so much percent carbon, so many percent of hydrogen, so much percent of oxygen. And then from that, we would go in and start doing empirical formula sort of calculations. The way that this instrument actually works is on the inside of this instrument is a flame. It will simply pull the sample into that flame. Once again, electrons excite up, drop back down, emit photons. It looks for very specific photons associated with a given element. And it'll simply say, oh, well, hey, you know what? There goes a photon that's only associated with hydrogen. Therefore, there must be hydrogen inside that compound. There must be only carbon inside of here. But it's looking at, once again, that unique spectrum associated with that element in that case. Going back here. This next slide right here is a way in which they actually look at distant galaxies. A lot of times you'll hear, oh, well, in that distant galaxy, they got oxygen. They got hydrogen. Well, maybe they got water in this case. Well, a lot of times what they're doing is, once again, they're looking for very specific bands of colors that are associated, once again, with a given element. And once they find it in a distant galaxy, oh, well, hey, you know what? Once again, I can clearly see that element exists there. Now, if anybody's been paying attention to the news, last week, which was really cool. Unbeknownst to me, I didn't know we were going to get to this part of the notes and they were going to discover this, but I think somebody actually probably did it intentionally. They knew that I was going to get to this slide. So we're like, what we're going to do is we're going to look at a distant galaxy. Anybody hear about what happened?
They found a new color, right?
It wasn't a new color. Well, in a sense, not necessarily a new
wait.
color. But they're actually able to look.
Wait, wasn't it like the most probable sign of life or something like that?
Absolutely. The most probable sign of life. They found a planet that seemed to be conducive for life. Once again, they're not certain whether or not that life exists there, but let me explain why they're kind of coming to this conclusion with this particular planet. There is a compound that is produced here on Earth. And the only way that compound is actually produced is it's produced by living organisms. No other way. We can't man make it or female make it. It's just, once again, living organisms produce it. Well, when they looked at that distant galaxy and they looked at that particular spectrum that would produce for these compounds, they found that compound existing there. And the only thing they can deduce is, once again, there's a high probability there's some sort of living organism that exists on that actual planet that's producing the compound. Does it absolutely mean it has to be? It doesn't. It is some way possible that planet is somehow producing it. We just know here on Earth we can't do it. So we're suspecting that most likely that planet has some sort of organism that's producing that particular compound in this case. All right, continuing on here. This slide right here, the only thing I'm showing you with this slide is I'm going to show you kind of the new Bohr model. Once again, it's not the model that we accept. We know the quantum mechanical model is a true model. I'm just using this for simplicity's sake to illustrate something really quickly. So we got hydrogen. Hydrogen has our one electron. And basically what we do is I'm going to give it, oops, wrong way, I'm going to give it a quantum of energy. And of course, once again, as long as it gets the energy to take it to one of the given energy levels, it will go ahead and promote up. So there it goes, promoting up. Of course, according to the off-ball principle, the electron does not or should not exist at that higher energy state, so it should drop back down. And of course, when it does drop down, it's going to end up emitting, in this case, a photon. So there goes my photon coming out. Now, remember, the electron could transition to these other energy levels as well, just depending upon whether or not it received the right amount of energy. So there's multiple ways in which the electron can actually transition itself downwards in this case. And if we were to study the spectrum that's going to be produced based upon the electrons returning back down to these lower states, then we get a spectrum that looked kind of like this up here. But one of the things to point out is when we looked at hydrogen, and I showed you the spectrum, we said, hey, we should see red, we should see green, teal, we should see violet. But I see a lot more bands up here than the ones that were actually listed. And the reason why you're seeing a lot more bands here is this is, once again, the spectrum of things that we can see and things that we can't see. I told you that when it came to that actual glass tube that it got hot, and the reason why it got hot is there were photons of infrared radiation. There's also photons of visible. Where our focus on in this class is going to be is just, once again, the visible, because that's what we can see. But it doesn't mean that we don't have instruments, because we do have instruments. They can look at these photons right here. And I got an instrument in the back of the classroom that has a little tarp over top of it that will actually analyze in this region right here. It says, hey, I don't need to be focused here. I can be focused here. And guess what? No two elements share the same ultraviolet region either. They're going to have unique fingerprints that exist there. So the only thing I want to point out is that when we do get these photons being emitted, it doesn't have to just be visible. It could be in the infrared, ultraviolet, microwave, and so forth. All right. Moving on, yes.
Is this like how scientists like discover new colors like through elements?
When you say new colors, like
I guess I mean more like a while ago when they were like naming a bunch of the colors, like not common ones. Is that how they would like find them?
Yeah, like they engineered that like new shade of blue or whatever.
Yeah.
when they engineered it. When you're engineering, I mean, in theory, what you can do is a lot of times, like, if I want to produce that as a light, as a form of light, then what I'm going to end up doing is I've got to actually mix different colors together. So, for instance, I didn't go over this, but I'll just point out really quickly to kind of give you a sense of what's going on here. If I go back here, one of the things that I know is white light produces something that looks like this right here. If you ever go to the hardware store, you'll notice that when you look at white light, sometimes white light's a little bit more of a yellowish color, sometimes a little bit more of a crisp white color. It's like different shades of white. Well, a lot of times when it comes to these actual lights that they're producing, what they're doing is they're taking different elements and placing them inside of the actual tube. And when they place those different elements inside the tube, what starts to happen is they start to fill in kind of like these gaps right here. So this would fill in the gaps right here. And as you start to fill in more of the gaps, then what's going to end up happening is you're going to start getting something that's going to start looking more like white light. And that's why a lot of times when we talk about, anybody ever heard of like the halogen light bulbs? Once again, they're starting to fade out because LEDs are becoming more popular. The halogen light bulbs are made up of halogen gases. They put the halogen gases in there, and once again, they start to fill in these gaps. And as you fill in more and more of the gaps, it looks more and more like natural white light. So a lot of times if they're trying to produce, in this case, maybe some new color that they're going to shoot at your eyes, then one of the things they can do is kind of mix maybe two elements together to get that new shade of color that they're actually looking for in this case. All right, here we go. Oops, right here. So we're going to look at now really quickly is we're going to look at the relative size of atoms. When we talk about the relative size of atoms, what we're going to talk about is kind of just how big or how small the atoms happen to be. And one of the things that's going to happen tomorrow is you're going to have a homework assignment. In that homework assignment, I'm going to give you different elements, and they say, oh, that element is larger, or that one happens to be smaller. But before we can talk about the relative different sizes of the actual elements, we just got to look at a couple things first. First thing we're going to look at is when we talk about the actual size of the actual atom, we're going to base the size of the atom based upon its outermost electron. So when I look at an atom such as this atom right here, I might say, oh, its relative size is going to be somewhere right here. Just like if I had another element, let's just say hypothetically that element had electrons that were way up here. I'm going to say, well, the size of this atom is going to be a lot larger in this case. So we kind of go with those outermost electrons to determine the relative size of the atoms. Now, one thing to keep in mind, one of the things that is responsible for pulling the electron in towards the nucleus is going to be the protons. Protons are positively charged. It's like a magnet. It's like, hey, I'm going to pull that negative thing in towards, in this case, the actual nucleus. Watch what's going to happen here. If I have something such as hydrogen that has one proton and one electron, then I got like one magnet that's sitting here and is pulling that electron in towards the nucleus of the atom. If I look at helium, this electron right here feels the force of two protons pulling it towards the nucleus. The other electron feels the force of two protons pulling it towards the nucleus as well, which means that each one of those electrons is feeling two protons pulling it towards the nucleus, which means that they're going to get pulled in closer, which means that the size of helium relative to the size of hydrogen, helium is going to actually end up being a smaller element. And if you look at what I have right here, it simply says, hey, atoms. I got hydrogen, and it says 0.37A, which stands for angstroms. Angstroms is 10 to the negative 10. Now keep in mind, I'm not going to ask you what an angstrom happens to be. Only thing I want you to see is that, hey, I can clearly see that when it comes to hydrogen as being 0.37 angstroms versus helium as being 0.32 angstroms, I see helium is definitely going to be smaller. And once again, it's simply smaller due to the fact that we have more protons pulling on the electrons, and it's just doing a better job of pulling it closer to the nucleus, causing the atom to actually end up being smaller. Which leads us to our first trend. Our first trend simply says, as you move across the periodic table, the number of protons are going to increase, so therefore the strength of the nucleus pulling on the electrons is going to be stronger, and it's going to cause the atoms to simply get smaller in this case. So if we look at the periodic table I have right here, you'll notice that, hey, if I go from lithium across, lithium has 3 protons, beryllium has 4, 5, 6, 7, 8, 9, 10. The atoms get smaller and smaller as I move across the periodic table, and that's what you're going to see in this picture right here. As I move across, you're going to always notice that the sizes are getting smaller and smaller, and it's simply due to the increased number of protons. Hey, on a test, I can put that as a multiple choice question. Oh, you know what? As you move across the periodic table, the atoms get larger or smaller. The whole thing is say smaller. And it can go in and say, hey, the reason why is because the number of protons are increasing, therefore pulling electrons in closer to the nucleus of the atom. Just make sure, once again, you know that the trend is caused by the increased number of protons. Next thing we have to look at is what about going down the periodic table? Going down the periodic table, if we look at maybe just going down a family, and the family that go down is going to be the 1A family. Hydrogen has an electron configuration of 1s1. Lithium has an electron configuration of 1s2, 2s1. If I go to sodium, sodium has an electron configuration of 1s2, 2s2, 2p6, 3s1. If I go to potassium, potassium has 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Well, hopefully we can see what's going on. Hey, hydrogen, I got my outermost electron in the 1s. Oh, lithium, I'm way out here in the 2s. Sodium, I got my valence electron way out in the 3s. Potassium, look at me, I'm way out here as well. So what we're going to see is as we go down the periodic table, you're going to notice that the electrons, the valence electrons, are in higher energy levels. I'm in the 1s. Oh, I'm going down the periodic table, I'm in the 2s. If somebody was in the 3s, they're way out here. The 4s would be somewhere in here. So the size of the atom is going to increase because we're forcing the electrons to exist out in these higher energy levels in this case. And of course, that's going to cause the atom to simply balloon up. And that's why you see with hydrogen versus lithium, hydrogen's 0.37 angstroms, lithium 1.434 angstroms. And we can see it right here as well. The size of the atom is increasing as we go downwards, and it's decreasing as we go across. So, right here, what do we do? Atomic radius decreases because increased number of protons. And of course, the protons are responsible for pulling the electrons in. The atomic radius increases as we go down. I'm going to say, hey, because electrons are, let's say this, because the valence electron, let's go that route, are in higher energy levels. And of course, if they're higher energy levels, that simply means they're further away from the nucleus. All right. Now, tomorrow's homework assignment, one of the things we do is we give you different elements here. And all that you do is just look at the actual trend. I'm not going to give you anything on the diagonal. Either it's going to be something kind of going straight across, or it's going to simply be going down. And you'll kind of figure out, hey, which atom has to be larger or smaller in this case. What we're going to do today is we're going to go into what is known as the photoelectric effect. Help me out really quickly. Anybody know who is responsible for this equation right here?
Einstein.
Exactly, Einstein. So a lot of times you're walking around on college campuses, you'll see like, cool kids that have a little t-shirt on that have E equals MC squared. A lot of times they don't even know what the C squared, we know what C is. What's C? Speed of light, exactly. So we know it, but a lot of times you have students on the campus like, I don't even know what it means. It just looks cool in this case. Einstein, what's associated with them. Now, when you think about Einstein, Einstein did not get his Nobel Prize, in this case, for the E equals MC squared. He got his Nobel Prize actually for what is known as the photoelectric effect. And what Einstein was trying to figure out is he knew that when it came to an atom has, in this case, 7 energy levels. That's the maximum number of energy levels it can have, is 7. So the question he had is he knew that, hey, if I give the actual electron a quantum energy, that it can promote up so long as it goes to one of those specific energy levels. But the question he had is, what if I give it enough energy to take it beyond the 7th energy level? Would the electron take the energy and be ejected out? Or would the electron say, nope, I told you I can only exist on these energy levels, I will not accept that energy. And that's what he actually set out to take a look at. Let me point one thing out. When he was trying to figure this out, what he was doing is he was taking metals. And metals have a tendency of not really wanting to hold on to the electrons, not too important. But what he did is he simply took these metals and he started shining, in this case, light on the metal. And he would go, in this case, from red light, and he would go to like a orange, then yellow, then green, then blue, and then violet. So he's kind of going right down the spectrum here. And remember that down here, this is low energy. As we go upwards, it becomes more high in energy in this case. And what he was able to figure out is that, hey, as I started shining maybe just red photons on the metal, you know what? I don't see any electrons jumping out in this case. Maybe they're jumping up, becoming excited, and jumping back down, but no electrons are being ejected. He went over here to orange. Still saw no ejection of the electron. Went to yellow. Still didn't see anything. It wasn't until he got to the green light that all of a sudden he started seeing, in this case, electrons just jumping actually out of the metal. And it looks something like this right here. Once he got, to that green, electrons started to jumping out. Now, when he went further, he's like, okay, well, green is getting out. Let me go to blue. Okay, they were still jumping out. Let me go to violet, still jumping out. Let me go, in this case, to ultraviolet, still jumping out. Anything with energy greater than the green, the electrons are being ejected out of this actual atom. And this is known as the photoelectric effect. Now, let me point out why this is so important. I'm going to go back to conceptual physics. And if you remember in conceptual physics, we said that if we had something such as a piece of wire. So here goes my wire right here. And remember, in conceptual physics, we said, hey, if you had a whole bunch of electrons, they would kind of just be sitting here on this wire. And right now, the electrons are just kind of sitting there, they're not moving, so therefore I don't have any what? They're not moving, I don't have, I think about a river. A river, we have current. We don't have no current, right? Electrons not moving, I have no current in this case. Now, of course, if I can push this electron and cause these things to kind of shift down, then we get the electrons to move, and I got a current in this case. Okay, let's see what's going to happen here. Going back to this image. Once again, you're not responsible for knowing this. Kind of explaining something here. Basically, what's going to end up happening is when you shine this light on the metal is going to once again eject the electrons. As the electrons are ejected, they're going to land and deposit themselves right on that metal. And what's going to happen is when that electron comes in here, it's going to say, hey, excuse me, make room. And as the other electrons have to make room, they're going to have to shift down in this case, which is going to cause this one to shift. And then the next electron is going to come up here as well and deposit itself. And it keeps on causing these electrons to shift. Therefore, we've got a current in this case. And keep in mind, I told you to use visible light for this. So not all the visible light is going to work. Like the red part, no good. Orange, no good. Yellow, no good. Once until we got to the green and on, that this thing started kicking out. Where could this be utilized? Where could we use this light? Harness the light for energy.
Solar panels?
That's exactly it. He is actually the father of what is known as photoic cells. Photoic is a fancy word for saying solar panel. Photoic, photons in this case, and we got the cell. Now, if you look at it, I have up here on my desk a couple of old projects from different science fair projects. This one was pretty cool, actually. Well, actually, both was cool, to be truthful. Maybe eventually I'll show you the actual project, but she made what's called an algae raceway pond. It's really cool. When she first brought it to me, she's like, hey, I want to make this algae raceway pond. I'm like, what are you talking about, a raceway in a pond? But basically what it is, it's like this pond, and you put water in there, and you make it go through these little canals, and then what happens, the algae will grow. And as it grows quickly, you extract the algae, and then we were able to take the oil out of algae and produce a biofuel in this case. Matter of fact, I'll show it to you really quickly, just so you kind of see what it actually looks like. So out in like Arizona and places like this, they have, let's go here, I'll go here. So it looks like this right here. So you'll see kind of how they raceway pond, and what you'll notice is they have kind of this, which you'll see in this image right here, they got this big paddle that's kind of just pushing the water through, because you need the current to kind of push through. As you get it to go through, it gets the algae to actually grow at a faster rate. For her project, once again, she was making this biofuel, but she wanted to make fuel that was going to completely just take advantage of, once again, just our natural resources. So she used a solar panel to actually, and that's why you'll notice we have a little paddle on the back here. And then when it came to the algae raceway pond, she 3D printed it on a 3D printer. And we had to like 3D print a whole bunch of pieces, because if you looked at the 3D printer, you can only print something about that size. So we kept on printing little sections and she super glued it together. Put this inside there to get the water to kind of go through. Solar panels sitting right here. It was a pretty cool experiment. But the reason I'm pulling this out anyways is that if you look closely, you'll notice that for all solar panels, they always have this little metal piece that's going right down there. That's that wire that's going to catch the electrons and produce the actual electrical current. Even if you look at my smaller one, which I just had right here, and this one was a slightly different project. But you'll notice even on this solar panel, you'll still see little pieces of metal wire that's kind of coming across here. And if you can't see in the back, when you leave out, I'll leave it right here on the table. You kind of take a look at it. This student right here was actually Mrs. Greenhall's daughter. She went off to the Naval Academy, but she did a solar panel experiment as well. I'm trying to remember who did this one. Can't remember. It'll come back to me in a second. Can't remember if that's Caroline Macro, and she went off to UPenn. What was cool about her project? Well, it was cool. She got accepted to medical school coming out of visitation. So stepping out of visitation, she was already admitted to medical school. They have programs in which you can actually be admitted coming straight out of high school. Now, what was interesting about that particular program, she turned them down. I couldn't believe she did it, but she turned them down even though she got accepted. And that's because she got into another school that she really wanted to go to, and she still ended up becoming a doctor, which is kind of pointing that out. Here we go, continuing on here. Off on a tangent. All right. There we go. How much time do we have left here? We've got, oh, man. We got how much time?
A minute.
1 minute.
Less now.
Can we harness our energy to somehow cover more material in that 1 minute? No, we won't. So, we didn't talk about the exam in this class, did we? We did. All right, so remember, we don't have an exam, we didn't have that test. Anything else I would point out? Don't forget, that's going to be scheduled technically for Monday. Homework for tonight is easy. Homework assignment tonight is just a review. Tomorrow we should be able to finish up the chapter, and then once again on Friday we'll go over the answers to tomorrow's night's assignment, and then on Monday we're looking at having a test in this case. All right, I will see you tomorrow. Remember, you're heading off to Mass, so we're going to Mass now. In the Wellness Center. You're welcome.
I feel like I just lived like
All right, let's turn this thing off.
in the first 2 periods, yeah, I know. It's like 1 o'clock, but it's okay.
You're welcome. We'll go.